Valentine's Day?
Filled with homework.
Filled with homework. Okay, that's not what Valentine's is supposed to be filled with, but sorry. Okay. I guess I should ask, how about assignment 3? I'm expecting you guys to say, what? That's not due till Thursday. I haven't even looked at it yet, right?
I'm having a problem where it's running for over an hour and not getting done.
Ah, that's not good. Okay, so this is today.
Can you give us advice on how to make it not
This
run
is
for an
assignment
hour?
3 due date. Yes. First of all, first bit of advice for everyone, which precedes your question, is start early because these things will happen and you don't want to deal with them Thursday night at 11:59, that kind of thing. So this, assignment 3 will run, it will take about 100 times longer to run than assignment 2 because it's bigger, right? We're working in 22-dimensional space now, whereas before we were working in 2-dimensional space. How much bigger is that? Yeah, well, just to give you an estimate of it, how many pixels wide were there in assignment 2? 500 raised to the 2 power is that. That's a reasonable amount of computation. Now let's take 500 raised to the 22nd power, 22nd power. That's how much computation your computer would be doing if there were 500 positions for every puzzle piece in each dimension, which there is not. So let's reduce it down to 10 to the 22. Duh. Okay, 10 to the 22. Thank you for that calculator. That's still more computation than you can probably do in an evening, don't you agree? So why is this even going to work? Well, there's a lot of pieces that get in each other's way, marking all of these moves illegal. And if the moves are illegal, then you don't really need to explore all the sub-moves because that stops it. And so actually, the fact that there's not a lot of possibilities makes it tractable. I think people are getting solutions in 5 minutes or less. Is that about right for those of you who've got it working?
3.5.
3.5? Okay, 3.5 minutes, 10 minutes?
1 minute, 10 seconds.
1 minute, 10 seconds. Okay, so if you write nice code, you can do it really fast. Out of curiosity, those who have answers, how many moves does it take to solve this puzzle?
114.
114? Anybody beat 114?
That's what I got.
That's what you got too. It sounds like the answer is 114. Okay.
That puzzle in a game?
So you should. You should what? What was that?
That sounds like a really tedious puzzle for a video game.
Yeah. Well, that's why I coded it up. Is man, that puzzle really was whooping me, and I said, "The heck with this! I'm coding it up."
Isn't Professor Layton a game for kids?
It is, and in fact, 90% of the puzzles are just brain dead dumb, and it's really annoying to go through the game and just say "da da da," and then every once in a while you find a cool one, and it makes it all worth it. So, I'm not pitching Professor Layton. I have no need to sell that to you. I have no vested interest, no stock in the company. But the 1 in 10 puzzles that are fun, I think that makes it worth playing a game. I liked this one because it was hard, but I don't know, that's that. 100, what was it, 114? I should add that to the, okay. So at some point today I need to answer the question, what do you do if you get another answer? And I need to finish answering your question, so give me 1 second. Assignment 3?
Yes.
Sorry, I'm just going to do an instant update here. I think the answer takes about 114 minutes. There. Bam. In-class updates. The answer is on the hints page. Okay. And this is based on your code. I didn't even code it up. Well, I did long ago, but I've lost my code. And I don't want to do it again. And I'm a professor, so I don't have to. Okay. But I can access working copies and figure out what the answer is for sure. So here we go, 114. What do you do if it's taking too darn long? Why, help me out, why do you think it's taking too long? What would do that? Yeah, infinite loop in your code would obviously do it. If you're not checking where you've been, this is the, hopefully we've ironed that through in assignment 2, so I'm betting that's not it. But if you're not checking where you've been, you are hosed in this one.
Yeah.
I mean, if assignment 2 you were hosed, in this one you are hosed to the 22nd power hosed. So you absolutely have to check where you've been or it will not work. And surprisingly, Java makes it difficult to do that. You think you're doing it, but it doesn't unless you test your code a little bit. So test your code a little and make sure you really are checking where you've been. What's the next issue that would come up?
Following illegal paths.
Yeah, if you're allowing illegal paths, that would certainly slow you down. So you want to check that is your move valid thing actually makes valid moves. What's an easy way to test that? I'm not sure. Here's how I'd do it. I'd go take this code. So this is my visualizer, right? And right now, it just makes random moves and visualizes it. Have you run that code and seen what it does? Okay. So if you were to take your isValid move and just plug it into that code, that wouldn't take very long. And then you could, every time you do a random move, check if it's valid. If it's not, don't do it. And then you could click through a bunch of times and watch that the moves are all valid, and that would basically visually test it. Is that reasonable? There's probably better ways. That's the first thing that popped into my head. Seeing hand?
The downside of that being that if it says that an actual allowable move is not allowable, you won't be able to catch it.
That's a good point. Okay, how do you make sure your isValid doesn't say no on something that it should allow? That's a good question. Just don't make any coding mistakes. Okay.
So we don't have to test then?
Yeah. I guess you could systematically run through all possibilities. We know by human inspection there are 2 valid moves in this starting state, right? So you could easily write code that would check for all valid moves, and there better be 2 starting in this state. If you don't, then you've already found a bug. So there's a good starting point. Another thing is get in a couple of other states and make sure it finds them all. After you've spot checked 2 or 3 different states, I'd be pretty confident that it works. Is that too optimistic? I think I'd just go with it until there was really a problem, and then I'd have to
Is
get
there a
dirty.
better way of encoding the puzzle than having a 2D character array?
Ah,
Because part of me thinks
maybe
that's
yes and maybe no.
Because that part of me thinks that's why it's going so slow. Is a lot of 2D character arrays.
Okay. That would do it. So it depends what you mean by encoding the puzzle. There is the notion of state here, and I claim that you need 22 numbers to encode the state. So this is a character array of size 22. Are you saying is there a better way to encode it than that?
No, I was more wondering. I have a 2D character array that essentially has all the pieces and the positions they are on the board.
Okay, so
Because
you're
I'm-
storing all 100 characters per puzzle.
Yeah, because I'm not sure how I can check if a move's valid without knowing the shape of the pieces.
Okay. Fortunately, I have the benefit of a little prior experience on this assignment. We did it last year. Here's what I found. A lot of students tried a puzzle encoding in which every puzzle required 100 characters. You can see why. And a lot of them did it in which it required 22 characters. Everybody that did the 100 characters, with one exception, their computers ran out of memory and they told me that they couldn't solve the puzzle. So I'm gonna say that unless you're that one student who happened to be an amazing coder, it's not gonna work for you to store the whole 100 character version of the puzzle. You want to store the 22 character version of the puzzle per state. So I'm gonna go out on a limb and guess that's what's causing your performance issue.
But how do you know if a move's valid using that information though?
Right. So now the next question, how do you know if the move's valid using this information? When we're recording, I have to repeat your questions anyway.
Yeah.
So here we are. We have a state that looks like this, and I need to answer the question, is this move valid? What do you do? Notice I'm just repeating your question because that's actually a technique. I'm supposed to do that. How do you guys do that? Here's a state, is it valid?
Initialize the board, have the array of the original positions of pieces, add those offsets to the original positions of the pieces, and place them on the board.
Yeah, so essentially, let me restate in my own words, which are probably totally different. But you're going to have an array of 100 characters somewhere. And you could have 100 bits or 100 whatevers if you want. I just do characters because they're easy. I don't care if I waste a little memory. But I would only have one copy of that. It sounds like what you're doing is you're making exponentially many of them. If you only had one 10 by 10 array of chars, then you could reuse that same 10 by 10 array over and over and over every time you need to validate one representation of state. So essentially, here's a state, is it valid? Well, now I fill up my whole array, I answer the question, and then I abandon that array. Well, till next time. Here's another state, is it valid? Go back, fill up that same array again. Now I'm not using a lot of memory because I've only got 22 bytes per state and I'm reusing my 100 by 100 buffer. Okay, so don't store the shapes of the pieces or how many blocks are in each piece in your state. If you do, it will sink you. I know this because it sank everybody except for that one student. I don't know how he got it working, but he did.
32 gig of RAM.
Yeah, 32 gig of RAM. By the way, in Java, there is a command switch you can pass to it that will expand the size of your heap. So you can actually use crazy amounts of memory in Java, and it can actually work. I believe it's XMX.
Yes.
So if you want to run it, you say, instead of saying Java puz, you say Java dash capital X, lowercase m, lowercase x, 4G, to mean use 4 gigabytes of RAM.
I think it has to be capital G.
Okay, make that a capital G. And now if I had Java installed, or if I had a puz program in this folder, which I don't, it would now run and have a lot more memory to work with. By default, the Java heap is way too small, although I think it adaptively rescales it. Maybe? Does anybody know?
The max doesn't change, I don't think.
Okay. But if you code it up well, I think you don't even need to use this switch. That's just there in case you think you do. Just so you know that's there. Okay. Anybody else? Any questions on this assignment? Have you had any trouble or you think you can do it? Yeah.
Maybe I'm just like understanding it right, but we're using we're supposed to use the same are we supposed to use the same method as we did assignment 2?
Yes. But if by method you mean the same underlying algorithm, yes.
Okay. Well, what are we comparing between states? Because the puzzle knows, my code knows, this is the initial state of the first 2 bits in the array. This is where it wants to go, but I'm not sure how to tell it this state. You know, when we had the other side, you could tell, well, if it's darker, that's more costly.
Yeah. Let me answer what I think will answer your question. And if I miss your question, please repeat or clarify. but essentially, in assignment 1, you probably coded up uniform cost search, and I'll say this represents uniform cost search. And in here, in this box, you've got some kind of a, let's see, you've got a priority queue, which I'll use the letter Q for, and you've got a while loop, and you're going to push something into that queue, and then until you find the goal, you're going to do this while loop. And somewhere inside of here, you've got code that's going to try all the actions. You're going to try north, south, east, west. And for each of those neighbors, you're going to push them back into the queue. And you're going to check if your state reaches the goal. And you're going to go until it spans the whole space of the puzzle. That's about what your code looks like, right? Here's what I think you ought to do is over here. So I'm going to let the left side represent uniform cost search. And I'm going to let this side represent the problem. So the first thing I would do over here is I would add an interface for int count actions. Basically, this function would return, if I were doing assignment 1, this function would return the number 4. Why 4? Because there's 4 possible actions. And then I would add another method over here called void do action int I. And then this way, in my code over here on the left, when I'm trying to visit all the neighbors of a particular state, I would first call count actions and it would return 4, and then I'd say for I from 1 to 4, or from 0 to less than 4, 0 to 3, do action 0, do action 1, do action 2, do action 3. And that way I can essentially abstract away the problem from the uniform cost search. And then I'd probably have to have something down here like Boolean is goal, state S, something like that. And then I would implement this by comparing whether I've reached 400, 400, and let's see, is that everything we need? We're going to need a copy constructor here. So let's see. I need some representation of state, and that state needs a way to clone itself. So I guess that's what this state object is here that I was talking about. And that would be over here too, so maybe I'll draw a box to represent my state class. And I'll make sure the state class has a copy constructor. If I did all of those things, then I think I've separated the problem from my algorithm. Do you agree? Did I miss anything? So now, after we've separated the two things, now we move into assignment 3. And we suddenly find that this problem is totally different. What do we do for the state? Well, now we've got 22 chars to represent the state. What's the count actions going to do? It's going to return 44, I believe, right? Oh, we're also going to need to augment it a little bit. We're going to have to say bool is valid. So we'll add a method here that answers the question, is this a valid state? We didn't really need that in assignment 2, so you might have to kind of augment it a little bit. If you wanted to separate it, assignment 2 could basically answer true for all states as being valid. Except for if you run off the edge of the screen. In fact, that'd be a great way to test edge detection. So if x becomes less than 0 or greater than 499, or y is less than 0 or greater than 499, that would return false. In this assignment, is valid is going to take your state and basically draw the puzzle in that 10 by 10 array and find out if it's a valid state. In this assignment, count actions will return 44. And when you say do action, for each of those 44 values, I need to move the corresponding piece, which means find the right dimension and increment or decrement it in the state. Is goal In this case, all I need to do is check the first two numbers and see if the red pieces reach the top. And as long as I've separated them this way, such that I have the algorithm over here and the problem over here, now I claim it's super general code, and now it's just a matter of rewriting this part, and that part you don't even have to touch. Now that I've done all this talking, did I even come close to your question?
It was more a question of, you needs, well, it needs like a character to tell you how it's prioritizing what's in it, right?
Yeah, it does.
What exactly makes one state of the puzzle a higher priority? Like,
Yeah, what is the
I-
cost in this?
it seems like there's only one state of the puzzle that's any higher priority for me to feel like than others to solve.
Got it, okay. Well, in this case, I guess to answer the question, I have to ask, let's suppose there's two solutions, which one's better? Yeah, the one's better, right, yeah. Anyone that gets the red square out of there is right. Suppose I start by moving the blue piece to the right, and then to the left, and then to the right and the left, and I do that about 100 billion times. And then I move the pieces around to get the red thing out of there. That's a more costly puzzle than the most efficient one, right? So I'm just going to say the total number of moves is the cost in this case. In other words, yeah, your priority queue should sort by how many moves you've visited. As it's expanding the frontier, it will visit or each path of moving pieces. The longer that path is, it'll wait to explore that until all other possibilities have been explored of shorter length. And that way, by the time it finally solves it, it's guaranteed to be the shortest possible path. And that way you'll get 114 for your answer. If you accept any valid move, then it'll wiggle pieces around in all kinds of crazy ways, and then you'll just get lucky to get the red piece out of there. So if you take a lot more than 114 moves, you're not doing uniform cost search. I imagine if you just did random moves and iterated long enough, you might solve it. I don't know, the puzzle's hard enough, maybe not. But it might happen in your lifetime. You might get that red piece out, but it just wouldn't be an optimal solution. Does that answer your question now? Okay. Yeah.
Kind of tacking onto that, actually. So as we're is there an easy way to look at a state and say, how many moves did it take for me to get here? I mean, is it just like the difference of each position from 0? It seems too simplistic.
Well, let me put it this way. Here's assignment 2. Here's the MyState object in my pseudocode. And there's this member variable here called cost. And it basically tracks the sum of all the green pixel values that you've ever seen so far to get to this state. In assignment 3, that's going to be an integer, and you're just going to increment it every time you make a move. So essentially, is there a way to tell how many moves it took to get to that state? Well, yeah, it's right there. So you're just going to have to track that, and that's what your priority queue will sort on. So because this my state is considered part of the problem, not part of the solution. So the my state, it goes over here. And of course, this separation isn't something that even really has to be in your code, but it should if you write good code. That's just kind of a virtual separation to show how to separate the problem.
You mentioned randomness. Is there any benefit to and directly incrementing the pieces positions in your code versus just randomly moving a piece and then checking its value?
Well, if you run through all possible moves, then you guarantee you don't miss something. If you randomly pick 5 moves and try them, and then you pump that priority queue, there's always the possibility you missed one, and you'll get a suboptimal answer in the end. So kind of the whole benefit of uniform cost search. See, uniform cost search is not a very fast algorithm here, but it guarantees when it's done, there is no better solution than the one it finds. So just by virtue of the fact that we're doing uniform cost search, You need to be systematic and try every last possible action in every possible state, or else you're not doing uniform cost search. In the real world, there's a good argument for, hey, maybe you should just try a few and move on. And in the end, you'll probably find a decent solution anyway, and your cost will be way less. But it's not uniform cost search. So right now, be systematic. Okay. If there's nothing else, I think I'll leave it at that. I do want to ask, though, what types of problems can we solve with this, and what types of problems can we not? Could we do chess with this? Almost. There are some missing pieces. We haven't talked about how to work with an opponent, particularly if you assume you have an intelligent opponent. If we have an opponent who behaves in some deterministic manner, then this would solve it very nicely. What about controlling a robot? Could you control a robot with uniform cost search?
You had a map of the environment.
Yeah, so think about it for a minute. What would your state be in a robot?
Direction,
You'd have to
spacing.
kind of describe all the joints. A robot has, a joint here, and then, so the servo's in some position, and there's probably clampers on the ends of its hands, and you've got some open or closedness of each of those joints. And of course, robots never have knees because they have to walk like this. I don't know why they did that in all the old 70s movies of robots. You look at old Star Wars, they walk stiffly. But if you just count the number of joints they have and give them all numbers, that pretty much does the position of the robot, right? Unless the robot lives in a world, if it's not inside of a perfectly clean laboratory, then, well, now you need state to describe where the other things are, the things it's operating on. Suppose you're working with a robot that's supposed to fold laundry. How many numbers does it take to describe the exact position of a piece of cloth? It's kind of a hard problem, but if you had maybe 20 numbers, it's probably enough to describe the cloth reasonably well. Maybe not perfectly well, but imagine you described it reasonably well enough that you could do some math. I think you could solve it. What would count actions be here? Well, every joint could either go more closed or more open, right? You might have some weird joints, like ball joints, that can do funky motions. I don't know how many numbers it takes to do those. Let's just pretend those don't exist. I guess you can open and close your clampers. Basically, add it up, figure it out. Now, how about do action here? All the actions you could possibly do, you would tell it which action you want to do. Except now we're continuous space, so instead of just giving it an action, you probably have to tell it how much, right? With how much velocity should you increase the joint? Should you put 1 Newton of torque on it? Should you put 10 Newtons of torque on it? Is Newton even the right unit for pressure on a joint? I don't even know because I don't do robots. But
Torque is Newton meters.
torque is Newton meters? Okay. Newton meters, pretend I said that. But you could basically run through all the possible actions you could do. Or if your robot always moved at a constant rate, you could just use that interface. Is goal. Well, you could basically check, is the towel folded and lying neatly on the ground? Are the dishes washed? Does the dog walk? Is the house clean? Whatever your robot's supposed to do. What about invalid state? What would you do with a robot there?
If you're not bumping into something.
Yeah, basically the robot can't just fly. I mean, unless it can, in which case that's a valid state. But this is going to be really tough because you're going to have to enumerate all possible states. And the robot's going to try to explore things like make the towel just start folding itself, right? Because that's